This script explores how scientists detect planets beyond our solar system, highlights groundbreaking discoveries in exoplanet research, explains planetary formation processes, and discusses implications for finding life elsewhere in the universe. Detection methods have evolved from measuring subtle wobbles in stars to observing light dimming during planetary transits, enabling the confirmation of nearly 6,000 exoplanets to date. As we continue exploring these distant worlds, we're developing a deeper understanding of planetary diversity while advancing the exciting search for potentially habitable planets that could harbor life. Hello everyone, and welcome to another episode of our Exploring Science and Technology series. Today we're venturing beyond our solar system on an exciting journey to discover exoplanets, planets that orbit stars other than our sun. Just 30 years ago, we weren't sure if planets existed around other stars. Today we know our galaxy is teeming with them. But how do we find these distant worlds? What have we discovered so far? And could any of them potentially harbor life? In the next few minutes, we'll explore the ingenious methods astronomers use to detect planets trillions of miles away, highlight some of the most fascinating discoveries, understand how these planets form, and consider what makes a planet potentially habitable. So let's begin our journey hunting for Earth 2.0. Finding planets around other stars is incredibly challenging. Unlike stars, planets don't produce their own light. They merely reflect light from their host star, and that reflected light is billions of times fainter than the star itself. It's like trying to spot a firefly next to a lighthouse from miles away. So how do astronomers overcome this challenge? Let's look at three main methods they use. The first successful technique for finding exoplanets is called the radial velocity method. It's based on a simple principle. Planets don't just orbit their stars, stars also orbit slightly in response to their planet's gravity. When a planet orbits a star, it pulls the star in a tiny circle or ellipse. This causes the star to move slightly toward and away from Earth as the planet orbits. When the star moves toward us, its light waves get compressed, shifting toward the blue end of the spectrum. When it moves away, the light waves stretch out, shifting toward the red end. Astronomers use sensitive instruments called spectrographs to detect these tiny color shifts. If they notice regular patterns in these shifts, it's evidence of an orbiting planet. This method works best for finding large planets close to their stars, as they cause more noticeable wobbles. This method led to the discovery of the first exoplanet around a sun-like star in 1995, which we'll talk about shortly. The second method is called the transit method, and it's currently the most productive planet-finding technique. It works similarly to watching a solar eclipse. When a planet passes directly between its star and our telescopes, it blocks a tiny portion of the star's light, causing a slight but measurable dimming. By measuring how much light is blocked and how often these transits occur, astronomers can determine the planet's size and orbital period. NASA's Kepler Space Telescope used this method to discover thousands of exoplanets. Currently, the test mission, Transiting Exoplanet Survey Satellite, continues this work, scanning nearly the entire sky. The first planet discovered using the transit method was HD 209458b in 1999, which was also the first planet whose atmosphere was studied. The third method is direct imaging, actually taking pictures of the planets themselves. This is extremely difficult because of the overwhelming brightness of the host stars. Astronomers use special instruments that block the star's light, allowing the faint planet to be seen. Very few exoplanets have been directly imaged so far, but as technology improves, we expect this number to grow. Now that we understand how astronomers find these distant worlds, let's explore some milestone discoveries. The first confirmed exoplanets were discovered in 1992, but not around a star like our Sun. Astronomers Alexander Wolszczan and Dale Frail found two planets orbiting a pulsar, the dense, rapidly spinning remnant of an exploded star. This was surprising because pulsars are violent, radiation-filled environments where planets weren't expected to survive. The discovery that truly revolutionized our understanding came in 1995, when Michel Mayor and Didier Queloz found a planet orbiting a sun-like star called 51 Pegasi. This planet, now known as 51 Pegasi b, is about half the mass of Jupiter, but orbits extremely close to its star, completing an orbit in just over 4 days. This discovery was so significant that Mayor and Queloz were awarded the Nobel Prize in Physics in 2019. It was surprising because, at that time, astronomers thought giant planets could only form far from their stars, like Jupiter and Saturn in our solar system. 51 Pegasi b was the first of what we now call hot Jupiters, gas giants orbiting very close to their stars. Since these early discoveries, the number of known exoplanets has exploded. As of January 2024, we've confirmed 5,867 exoplanets. And this is just the beginning. Astronomers estimate that, on average, every star in our galaxy has at least one planet. Perhaps most exciting is the finding that about 1 in 5 Sun-like stars has an Earth-sized planet orbiting in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Understanding how planets form helps us make sense of the diverse worlds we're discovering. Let's see what we've learned about planetary birth. Planets form within disks of gas and dust surrounding young stars. These disks, called protoplanetary disks, contain all the building materials for future planets. The process begins with tiny dust particles, smaller than the width of a human hair, colliding and sticking together. These grow into pebbles, then rocks, and eventually planetesimals, the building blocks of planets. Where in the disk these planetesimals form affects what kind of planet they'll become. In the colder outer regions, far from the star, water can freeze, and ice particles help build the cores of gas giants like Jupiter and Saturn. These planets form relatively quickly, within the first 10 million years of a star's life. Closer to the star, where temperatures are higher, rocky planets like Earth form. Without the help of ice, these planets grow more slowly, often taking tens of millions of years to reach their final size. What's fascinating is the incredible diversity we're discovering. Some systems have giant planets orbiting closer to their stars than Mercury orbits our Sun. Others have super-Earths, or mini-Neptunes, planet types that don't exist in our solar system. This diversity is teaching us that planetary formation is a complex process with many possible outcomes. Our solar system, it turns out, is just one arrangement among countless possibilities. Now to the question that drives much of our fascination with exoplanets. Could any of them harbor life? What makes a planet habitable? When scientists search for potentially habitable planets, they consider several factors. First, they look for planets in the habitable zone, not too close to their star, where it's too hot, and not too far, where it's too cold. This zone is where liquid water could exist on a planet's surface, which is crucial for life as we know it. Second, they consider the planet's size and composition. Rocky planets like Earth are more likely candidates than gas giants. Third, astronomers are developing ways to study exoplanet atmospheres, looking for gases like oxygen that might indicate the presence of life. Several promising candidates have already been identified. Some of the most interesting targets are planets orbiting red dwarf stars, which are smaller and cooler than our Sun. These stars are the most common type in our galaxy, and their habitable zones are closer to the star, making planets there easier to detect. However, we're still in the early stages of this search. The holy grail for astronomers is to find an Earth-sized planet in the habitable zone of a Sun-like star within 30 light-years of Earth. Such a planet would be close enough that future generations might actually be able to visit it. So what's next in the exciting field of exoplanet hunting? New telescopes and instruments are being developed specifically to find and study Earth-like planets. These will allow us to examine exoplanet atmospheres in detail, looking for potential biosignatures, chemical signs of life. Meanwhile, we're also exploring worlds within our own solar system that might harbor life, particularly the moons of Saturn, Titan, and Enceladus, as well as Mars, which once had abundant liquid water on its surface. From the first confirmed exoplanets just 3 decades ago to nearly 6,000 known today, our understanding of planets beyond our solar system has undergone a revolution. We've developed ingenious methods to detect these distant worlds, witnessed the incredible diversity of planetary systems, and gained insights into how planets form. Each new discovery brings us closer to answering one of humanity's most profound questions: are we alone in the universe? While we haven't found definitive evidence of life beyond Earth yet, the sheer number of planets out there and their incredible diversity gives us reason to be optimistic. As we continue to explore the cosmos, we're not just learning about distant worlds, we're also gaining a deeper appreciation for our own planet, the only world we know so far that harbors life. Thank you for joining me on this journey through the fascinating field of exoplanet hunting. If you enjoyed this video, please like and subscribe for more science and technology content. Until next time, keep looking up.